morning friends. In chapter 13 nuclei up to the 13.15 numerical of exercise we discuss. Now today 13.18 we discuss 13.19. How long an electric lamp of 100 watt be kept glowing by fission of 2 kg of deuterium? Take the fission reaction 1H2 plus 1H2. So here we obtain the 2 unstable helium plus N plus 3.27 mega electron volt energy is released. Right? Okay. Now there is the most important numerical also in MCQ type question and also for theory purpose, that means the 3 marks numerical. Here the 2 deuterium are fused to form the unstable helium nucleus and 3.27 MeV energy is released. Right? With help of this energy released, a bulb of 100 watt, how much long give the light or the glowing? We have to calculate the time to consume that much energy by the bulb of 100 watt. For that purpose, first we have to find out how many numbers of atoms in 2 kg deuterium. Right? The energy released due to the fuse of the 2 deuterium atom is this 3.27. So how much energy is released due to the number of atoms already present in 2 kg of deuterium? Okay. After finding the number of atom and total energy released due to the 2 kg of deuterium. So here the lamp is given of 100 watt. That means it consumes the 100 joule energy per second. Whatever the energy we obtain due to the 2 kg deuterium, to consume that much energy, how much time is taken by the bulb? So this way we can find out the time for which the bulb is on due to the fusion of 2 kg deuterium. For that purpose, number of atoms in deuterium is numbers of atoms in 2 gram deuterium is equal to Na. That is the Avogadro number. Therefore, the numbers of atoms in 2000 gram deuterium is equal to N. We have to find out this. Therefore, N is equal to Na into 2000 upon 2 gram. That means the 6.023 into 10 is 223 into 2000 upon 2. 2 cancel. Therefore, N is equal to 6.23 into 10 is 226 atoms per gram. These are the numbers of atoms in 2 kg deuterium. Now, when the 2 deuterium atoms are fused, the energy released is 3.27 MeV. Therefore, the total energy released due to that much atom are fused. When 2 atoms of deuterium are fused, energy released is equal to 3.27 MeV. Therefore, total energy released from fusion of n deuterium atom is equal to there is a 3.27 MeV energy released due to the fuse of the two deuterium atom. Therefore, energy released per deuterium atom is equal to 3.27 by 2. That means the 1.635 MeV due to the single deuterium atom. Therefore, total energy released is equal to 1.635 MeV. That means the 10 is to 6 convert into joule. 1.6 into 10 is to minus 19. There is the conversion of mega electron volt into joule. Into number of atoms. Number of atoms is 6.023 into 10 is to 26 atom. That much joule. Therefore, 15.75 into 10 is to 13 joule energy is released. That is the total energy released. Right? So that much energy is produced due to the fuse of 2 kilogram of deuterium. Now, how much long the bulb is consumed, or the bulb of 100 volt. For that purpose, the total energy consumed by the lamp. Now, energy consumed by lamp per second is equal to 100 joule. Because the watt is given, 100 watt power is given. Power, that means the energy consumed per unit time. Therefore, time for lamp glowing is equal to total energy obtained by divided by energy consumed by lamp. Therefore, total energy produced is 15.75 into 10 is to 13 divided by 100. So we obtain the 15.75 into 10 is to 11 joule. Convert into the electron volt. Therefore, 15.75 into 10 is to 11 upon 1.6 into 10 is to minus 19. Just minute. Here we obtain that is the time for lamp is glowing. So that much second. Because the ratio of the energy, total energy obtained from the 2 kilogram deuterium divided by energy consumed by the lamp per second. So that is the time for which the lamp is glowing. Now divided by, here we convert this second into year. So we know that the watt here is equal to 3.154 into 10 is to 7 second. Therefore 15.75 into 10 is to 11 divided by 3.154 into 10 is to 7. So 4.99 into 10 is to 4 year we obtain. So this lamp is glowing 4.99 into 10 is to 4 year due to the fuse of 2 kilogram of deuterium. Again, this numerical is most important. How long an electric bulb of 100 watt be kept glowing by fusion of 2 kg of deuterium. Take the fission reaction as 1H2 plus 1H2, that means the two deuterium atoms are fused to produce the unstable helium nucleus plus neutrino plus 3.27 MeV energy. First, we have to find out the number of atoms in 2 kg deuterium. So, in 2 gram deuterium, the numbers of atoms is equal to Avogadro number. Therefore, in 2 kg, that means the 2000 gram deuterium, number of atoms N is equal to Avogadro number into 2000 upon 2. We obtain N is equal to this 6.023 into 10 raised to 26 atoms per gram. Clear? Okay. When the two atoms of the deuterium are fused, energy released is 3.27 MeV. Therefore, energy released per atom is 3.27 by 2, 1.635 MeV. Total number of the deuterium atom in 2 kg is this N. Therefore, total energy released from 2 kg deuterium is 1.635 to 10 is to 6. There is the mega electron volt, therefore convert into electron volt. Convert into joule, we multiply the 1.6 into 10 is to minus 90. And number of deuterium atom is 6.03 into 10 is to 26, that much joule. Therefore, 15.75 into 10 is to 30 joule energy is released due to the 2 kg of deuterium. Okay. Now, the length of bulb or the length of watt, 100 watt is given. That means the energy consumed by the lamp per second is 100 joule. Now, the time for lamp glowing is equal to total energy obtained divided by the energy consumed by the lamp. Total energy obtained is 15.75 into 10 is to 13 joule divided by 100 joule. So there is the second 15.75 to 10 is to 11 second. This time is, we convert second into year, therefore this quantity is divided by 3.154 into 10 is to 7 second. Therefore we obtain this answer in year. So there is the time. So lamp of the 100 watt is glowing for 4.99 into 10 is to 4 year. Okay. After that, calculate the height of the potential barrier for a head-on collision of the two deuterions. The hint is given. The height of the potential barrier is given by Coulombian or the Coulomb repulsion between two deuterions. When they just touch each other, assume that they can be taken as the hard sphere of the two femtometers. So here we consider the deuterium atom like this way. The radius is this capital R, 2 femtometer. So first we have to find out what is the potential energy of every deuteriums. Right? For that purpose, first the charge on deuterium is the same as the charge of electron. The radius of the deuterium is R is given the 2 femtometer 2 FM. Right? When the two deuteriums are collides head-on, the distance between their center is equal to R plus R, that means the 2R. So in this situation, what is the potential energy is this? Okay. For that purpose, the charge on deuterium Q is equal to 1.6 into 10 is to minus 19 coulomb. The radius of atoms I is equal to 2 FM is equal to 2 into 10 is to minus 15 meter. When two deuterium collide head on. The distance between their center is small r is equal to twice of r, like to this manner. There is the center. That means the 2r, that means the 2 into 10 is to minus 15 meter. That means the 4 into 10 is to minus 15 meter. There is the separation between the center of the atoms of the two atoms of the deuterium when the head-on collision is take place according to the given hint. Now, the potential energy of deuterium is equal to K into Q1 Q2 upon R. We know the value of Q, K, 9 into 10 is to 9, twice of or the 1.6 into 10 is to minus 19 whole square upon R, separation between their center, 4 into 10 is to minus 15, 4 into 10 is to minus 15. So we obtain the 5.76 into 10 is to minus 14 joule. Convert into the electron volt. Convert into the electron volt. Therefore, there is divided by 1.6 into 10 is to minus 19, that much electron volt. Therefore, 3.6 into 10 is to 5 electron volt is obtained. Right. Therefore, 360 kilo electron volt. That is the potential energy of system of two deuterium atoms. Right. Therefore, potential energy of every deuterium atom is equal to 360 kilo electron volt by 2. That is the 180 kilo electron volt. Therefore, the height of potential barrier for a system of two deuterium atoms. Therefore, the height of potential barrier for a system of two deuterium atoms is equal to 360 kilo electron volt. That is the answer. Because according to our question that is given, the hint is given, the height of the potential barrier is given by the Coulombian repulsion between the two deuterium when they just touches to each other. In situation of these two atoms are just touches to each other, at that time their centers are at distance small r is equal to 2r. In this situation, what is the potential energy? This potential energy is the height of potential barrier. We calculate the potential energy by using the equation K, Q1 Q2 upon R. Substitute the value of K, 9 into 10 is to 9, and charge of deuterium is 1.6 into 10 is to minus 19. Right? Divided by 4 into 10 is to minus 15. Thus we obtain the 5.76 into 10 is to minus 14 joule. Convert into the electron volt. For that purpose, we divide it by 1.6 into 10 is to minus 19. Therefore, 3.6 into 10 is to 5 electron volt. That means the 360 kilo electron volt. That is the potential energy of system of two deuterium atom. Therefore, the potential energy of every deuterium atom is 180 kiloelectron. Now, according to the hint, the height of potential barrier is equal to the potential energy of system of two deuterium atom is equal to 360 kiloelectron. Now, the last numerical of exercise of this chapter, from the relation R is equal to R0 A is to 1/3, where the R0 is constant and A is mass number of nuclei, so that the nuclear matter density is nearly constant, that means the independent of A. In short, we have to prove that the density of the nuclei is not depends on the atomic mass number or the A. Clear? For that purpose, the mass of nucleus is capital M is equal to average mass of nucleus into atomic mass number. Here the M is equal to average mass of nucleus. Average mass of the nucleus. And volume of nucleus is V is equal to 4 by 3 pi R cube. 4 by 3 pi R cube. Now we know that the R is equal to, relation is given 4 by 3 pi R cube. That means the R0 A is to 1/3 whole raised to cube. Therefore, volume V is equal to 4 by 3 pi as it is R0 cube into, right? Therefore, nuclear density rho is equal to mass, nuclear mass upon volume is equal to ME upon 4 by 3 pi R0 cube A. A cancel. Therefore, the nuclear density rho is equal to 3m upon 4 pi R0 cube. Here 3 is constant, m is average mass of the nucleus is also constant, 4 constant, pi constant, R0 is also constant, therefore that is constant. That means rho is independent of A. Is independent of A. Again, the mass of the any nucleus is equal to average mass of the nucleus into atomic mass number. That means the m into it. Now, the volume of nucleus V is equal to 4 by 3 pi R0 cube. 4 by 3 pi R cube. R is equal to R0 A is to cube. Substitute the value. Therefore, we obtain the V is equal to 4 by 3 pi R0 cube upon A. Therefore, the nuclear density rho is equal to mass upon volume. Mass is equal to m into A upon 4 by 3 pi R0 cube into A cancel. Therefore, 3m upon 4 pi R0 cube. So here all quantity are constant. Therefore, nuclear density is constant. Nuclear density is constant. That is independent of the atomic mass number